This is MW Penn, and I've brought Sam along to teach us how to find equivalent fractions. Sam is really good at adding fractions, so he'll be a great help. Remember that in our last session, we learned that adding fractions was the same as adding any other numbers. For example, if we have 1, 2, 3, 4 fourths of a square, and add 1, 2 more fourths of the same square, what we have is 4 fourths plus 2 fourths, or 6 fourths of a square. We can even count them up. But we also know that we can divide a square, or anything else really, into fractional parts in many different ways. We can look at this square and realize that we can divide it into 2 equal parts, or 1/2, 3 equal parts, or 1/3, or 4 equal parts, or 1/4, and of course many other ways. So, since the fractions are different sizes, how can we add some of those 1/4 parts to some of those 1/3 parts? Here we have 3 fourths plus 2/3. 3 fourths plus 2/3 equal what? We know 1/3 of something is bigger than 1/4 of the same thing, so we're not adding equal pieces. We couldn't just count them up or add them together. They're different. We can't count 1, 2, 3, 4, 5 somethings when they're not the same thing. But remember, in our last session, we learned that we can divide a square, or anything else, into equal parts in many different ways. And there are some divisions that can be equivalent to both 1/4 and 1/3. And we also learned that adding is easy if all the pieces are the same size. Remember how we added? We divided the square into 12 equal parts and realized that 3 of those parts together equaled 1/4 of the square, and 4 of those parts together equaled 1/3 of the square. Well, then all we had to do was add 12ths. 3 12ths plus 4 12ths equals 7 12ths, so that 1/4 plus 1/3 equaled 7 12ths. So now our only problem is finding divisions of the square that can equal all the numbers we're trying to add. For example, suppose we wanted to add halves and fifths. Might we find divisions of the square, parts of the square, that would equal both halves and fifths? And if we're adding halves and fifths, we find that they can both be represented in tenths. Therefore, we can find tenths that are equal to 1/2, and tenths that are equal to 1/5. 1/2 is equal to 5 tenths, and 2/5 is equal to 4 tenths. Our problem is solved. 5 tenths plus 4 tenths equals 9 tenths. So 1/2 plus 2/5 will equal 9 tenths. In truth, it's quite easy to find these equivalent fractions because the denominators of equivalent fractions always share the same factors. If a fraction is equivalent to 1/2, it will have a denominator divisible by 2. If a fraction can be equivalent to 1/7, it will have a denominator divisible by 7. If a fraction is equivalent to 1/3, it will have a denominator divisible by 3. This always holds true. If a fraction is equivalent to 1/11, it will have a denominator that is divisible by 11. And if a fraction is equivalent to 1/5, it will have a denominator that is divisible by 5. So this bears repeating. The denominators of equivalent fractions always share the same factors. Let's try this out. If we want to add 1/3 and 2/5, we know that we'll have to find equivalent fractions for both. And now we know that these equivalent fractions will share a denominator that is divisible by both 3 and 5. That is, it will be a denominator that has both 3 and 5 as factors. How can we find this number? Well, if we multiply 3 and 5 together, the result will be a number that is divisible by both numbers. That only makes sense. 3 times 5 equals 15, so if we use 15 as a denominator for equivalent fractions, we see that 15 is divisible by 3, 15 divided by 3 equals 5, and 15 is divisible by 5. 15 divided by 5 equals 3. 1/3 actually equals 5/15, and 2/5 equals 6/15. If we add together 5/15 and 6/15, the result is 11/15. So 1/3 plus 2/5 equals 11/15, and we have our answer. Let's try that again. Suppose we want to add 1/2 and 2/7. If we find equivalent fractions for both 1/2 and 2/7, we know that these equivalent fractions will have a denominator that is divisible by both 2 and 7. But if we multiply 2 times 7, the result is 14, and 14 is divisible by both. It has both 2 and 7 as factors. 14 divided by 2 equals 7, and 14 divided by 7 equals 2. We find that 1/2 is equal to 7/14, and 2/7 is equal to 4/14. Now all we have to do is add 7/14 and 4/14, and our answer is 11/14. So to find a common denominator, we simply have to multiply the denominators of the fractions we're adding together. The result will always be a common denominator. But that's only the denominator of possible equivalent fractions. How do we find the exact equivalent fraction? Now here is where Sam gets very clever. Remember this from our session on adding fractions? Some fractions are actually equal to 1. 15/15 is the same as 2/2. It's the same number as 3/3 and the same number as 10/10. They all represent 1. The whole, the unit. 15/15 equals 1. 3/3 equals 1. It means that we've divided a unit into 3 equal parts, and we have all 3 of them. We have the entire unit. 10/10 equals 7/7 equals 1. But what do we know about this number 1? The unit, the whole, 1. We know that 1 is the multiplicative identity. It means that if we multiply any number by 1, it doesn't change the number. 8 times 1 is 8. 10 times 1 is 10. 1/4 times 1 is equal to 1/4. 1 is the multiplicative identity. Sam likes using that word. but it's really a big word for a simple idea. Anything multiplied by 1 does not change. When we wanted to add 1/2 and 2/7, remember that we multiplied 2 times 7 to find a common denominator, and we found the common denominator of 14. But how will we find the numerator? Well, Sam will tell us. If we want to find equivalent fractions for both 1/2 and 2/7, fractions that share a common denominator, we could multiply each fraction by 1 in the form of either 2/2 or 7/7. The result would be equivalent fractions with a common denominator. 1/2 plus 2/7 would equal 7/14 plus 4/14, and the result would be 11/14. Let's try that again. Let's add 1/3 and 3/4. First we'll multiply 1/3 by 1 in the form of 4/4. The result is 4/12, a fraction equivalent to 1/3, but with the denominator of 12. 3/4 times 3/3 equals 9/12. Remember, we're multiplying 3/4 by 1, so 9/12 is equal to 3/4. And when we add 1/3 and 3/4, we're doing the same thing as adding 4/12 to 9/12, and the answer is 13/12. Let's try it one more time. 2/3 plus 3/5. We'll multiply 2/3 by 1 in the form of 5/5, and we will find an equivalent fraction, 10/15. We'll multiply 3/5 by 1 in the form of 3/3. The answer is 9/15, a fraction equivalent to 3/5, but with a denominator of 15. Now we simply add 10/15 to 9/15, and the result is 19/15. Equivalent fractions with a common denominator. So what have we learned so far? We've learned that when we want to add fractions with different denominators, we should find equivalent fractions that share a common denominator. Then we just have to add up the pieces. It's the way it's always done, and the Common Core State Standards have an algorithm for doing this. I'm going to share the algorithm with you, and you can decide if you'd like to use it. The algorithm is A over B plus C over D equals the quantity AD plus BC over the denominator B times D. The algorithm will work every time. But Sam has a problem with it. First of all, Sam has a very difficult time saying the word algorithm. And he also thinks that there are a lot of algorithms to remember. Sometimes he does forget which algorithm to use. So let's go back to our method of finding equivalent fractions that share a common denominator. If we take the algorithm apart, we'll see that all we're doing is multiplying each fraction in an addition problem by 1 in the form of, now listen carefully, 1 in the form of the denominator of the other fraction over the denominator of the other fraction. Let's look at it carefully. If we're adding A over B to C over D, what we do is multiply A over B by the denominator of CD, or D over D. And then we multiply C over D by the denominator of A over B, that is 1 in the form of B over B. The result of this multiplication is AD plus BC over the denominator B times D. I think maybe we should look at this in number form. Let's add 2/3 and 1/4. Well, according to the algorithm, we will multiply 2/3 by 1 in the form of 4/4. And then we will multiply 1/4 by 1 in the form of 3/3. The result will be the quantity 2 times 4 plus the quantity 3 times 1 over 3 times 4. Yes, I can see why Sam has problems with the algorithm. But if we look at the numbers, it all seems much simpler. Let's practice it a few times. Suppose we want to add 1/5 and 1/7. Well, we just simply multiply 1/5 by 1 in the form of 7 sevens. And then we multiply 1/7 by 1 in the form of 5/5. The result is 7/35 plus 5/35, equivalent fractions with a common denominator. And then we just add up 35ths. We find we have 12 of them. If we're adding 2/5 and 3 sevens, when we multiply 2/5 by 7 sevens, we find an equivalent fraction of 14/35. That is, 14/35 is equivalent to 2/5, but it has a denominator of 35. We'll multiply 3 sevens by 5/5 and find an equivalent fraction, 25/35. Now we're adding fractions that share a common denominator, and the result is 39/35. If we're adding 1/3 and 1/4, we'll multiply 1/3 by 1, that is, not changing its value at all, because we're multiplying it by 1, but we're multiplying it by 1 in the form of 4/4. We'll add that to 1/4 multiplied by 3/3. And what we're really adding is 4/12 plus 3/12. The answer is 7/12. But suppose we're adding 2/3 and 3/4. 2/3 times 4/4 yields the fraction 8/12. It's a fraction equivalent to 2/3, but with a denominator of 12. We're adding 3/4 times 3/3. 3/4 times 3/3 are 9/12. We add 8/12 and 9/12, and our result is 17/12. 17/12 is the same quantity as 1 and 5/12, but that's another lesson. Sam, I think, is getting tired. It's interesting that that last number, 17/12, is actually the same number as 1 and 5/12. That is, a unit with 5/12 left over. We sometimes call that a mixed number, and it's very frequent that we go back and forth between fractions and mixed numbers and fractions. You might want to learn how to convert them. But I think right now we'd better leave it as it is because Sam is quite tired. This slide presentation is a production of MathWord Press, teaching mathematics through literature. Triangle Prince and Polygon Princess are taken from the book Square Bear, A Fairy Tale of Polygons, written by me, MW Penn, and illustrated by Daphne Firos.